Welcome to Advanced Reverse Engineering. There's homework due on the 21st of September, namely it's due now, and that is to write the file reverser. So hopefully you all were able to do that and this assignment made sense to you, and that's great. So I'm going to check your code and see how it goes. There's no need to go over all this. I think you all know what you needed to do. Let's talk about basic blocks. So a basic block is a linear code sequence that doesn't have any branches in except to the entry of the basic block, and it has no branches out except at the exit or the end of the basic block. Basic blocks form the vertices in a control flow graph. So a basic block ends when the linear control flow ends. Now that's going to be at a conditional branch, like some kind of jump, like jump not equal or jump less than or jump not above. Or a jump instruction, because that will take you to a different address somewhere, so a jump. At a return, and that could be an I return, return from interrupt, or just a plain return, or at a halt. A basic block also is going to end on encountering the start of another basic block. Now why is that? Remember, a basic block only has one entry, and that's at the top of the basic block. So if we encounter another basic block, presumably something is jumping into that address, not just us flowing into it. And so we can't have multiple entries, so we have to terminate our basic block when we encounter the start of a new one. Now, the basic blocks can be organized into a control flow graph. The vertices are going to be the blocks, and the edges between the basic blocks will be the branches and the jumps. So basic blocks are really common. You'll see them used everywhere. The basic block algorithm is pretty simple. In pass 1, you will identify leaders. What's a leader of a basic block? Well, it's the first address of a basic block. An address is going to be a leader if it's just the first instruction, right? The address of the entry point is always going to be the address of a leader because that's going to be where the program starts. It's going to be a leader if it is the target of a conditional or an unconditional branch, right? Jump not above to an address, that address is going to be a leader. Jump to an address, that address is going to be a leader. If it's the address immediately after a conditional branch, it's also a leader. Well, why is that? Well, the conditional branch can take you away and point to another leader. But if the branch isn't taken, you flow to the next instruction, which has to be a basic block leader. Or if it's a target of a call. So what we would do is we would go through, do pass 1, identify all the leaders we can identify, and then in pass 2, we collect up basic blocks. So starting from each block leader we identified, we collect the sequence of instructions until we get to the next basic block leader or a terminator, like a conditional branch or a halt or whatever. And that's how that will work. Instructions that will terminate a basic block are jumps, halts, returns, I returns, conditional branches, and looping constructs. Things that break the straight line control flow. Call and syscall don't terminate the basic block because they will typically return and you'll flow forward to the next instruction. So let's apply the algorithm here. Here is some code, and let's apply the basic block algorithm to it. We're going to start at the top, so the very first thing, 6fox27, is going to be a leader just because it's the first thing in there. So we'll put a little red arrow by it, and we'll take a look at the instruction. And that instruction says call 46D0. So 46D0 has to be a leader because it's the target of a call. And we'll save it for later, but it looks like it's outside the scope of our little piece of code here. So here's our current set of things. First instruction is 6F27, that's going to be a leader, and 46D0 is going to be a leader. So let's move down to the next line and take a look at it. That has a move. We're moving a value into RDI. That's not anything that changes the control flow, so it's not going to be a leader. The next line, oh, look, we have a call. Call 0x46D0. Well, the call itself is not going to be a leader, but 46D0 will be, but it's already in our list, so there's nothing to do here. Nothing to add to the list. It's not that this line, 6Fox30, is not a leader. Let's go on. We'll add another move. This is not a basic block leader, so let's go on. Another call. Okay, this call points to something that's in our listing. If you look down near the bottom, it points to 6Fox70, which is down there where that red arrow is. So that's a basic block leader. So let's put it on the list. So we add it to the list, which now has 3 things in it. And let's keep going. The next instruction is a move. Not a basic block leader and doesn't add one. The next one's load effective address. Nothing to see here. Compare. Nothing new here. Now we come to a conditional branch. So we jump if equal to 6Fox60, which is in our listing. So that is in fact a basic block leader. We put a red arrow by it and we add it to our list. But in addition, we might not take the conditional branch, which means the next instruction, the next address, 6Fox51, is also a basic block leader, and so we'll have to add it to the list as well. And so now we have 5 things in our list. Continuing on. Pop, we already know this line is a leader, but pop by itself doesn't add any information. And now we encounter a jump. Jump to 4CD0. So 4CD0 is in fact a basic block leader. Now the comment over there says it's already on the list. It's not. I got confused when writing this. It's not 46D0, it's for Charlie D0. I apologize. Another error. These slides have too many errors in them. I've got to fix them. But that does indicate that that would be another basic block leader. And notice here this jump is going to terminate our whole process. Where do we go after this? Well, we could keep going. We could look at this no op, and that doesn't tell us anything. We can look at the pop. That doesn't reveal anything. Next thing is a return. Returns terminate basic blocks, but they don't tell us where a new one is, so we'll keep going. Another nop, a compare, a push, and then finally a jump if equal to 6Fox9D. So we would add 6Fox9D to the list. It's not in our little listing here, but it is a potential basic block leader. And we add the instruction after the conditional branch, 6Fox7B. That also gets added to the list. So we put a little red arrow by it. We move on. That's our new list of those 7 things. We then look at the XOR. It's the last thing in our scope. Nothing to see there, and we are done. So we wind up with those 7 leaders, only 5 of which are in the scope of our little piece of code, and they're all indicated by those red arrows. Now, for each basic block leader, we're going to collect up the instructions that make up that basic block, terminating when we reach something that modifies the control flow. So let's go do that. That turns out to be super easy. For that first basic block, we have a call, move, load effective address, compare, and then a conditional branch. That conditional branch terminates the basic block because control flow goes somewhere else. The next one, beginning with pop RBX, includes the jump, and that terminates it because the control flow again goes somewhere else. The next one is pop RBX return. Return terminates that one. Compare, push, and jump if equal. The jump if equal terminates that one. And then finally, we have a basic block that consists of just the XOR, terminated because we've run out of instructions. And there we go. We wind up with those 5 basic blocks. Okay? This tells us where code is likely to be. It is what we would call a reachability analysis. How do I get to 6Fox60? Well, I may get there by this jump right here. Do I get there by this jump? I don't know. It could be that the code above this is engineered in such a way that that branch is sometimes taken, always taken, or never taken. In other words, I could be confused by this into adding something to reachability that isn't actually reachable. So, your mileage will vary. This is a naive algorithm. It's easy to implement. It runs fast, but it may not give us the exact correct picture of what's present in the code. Notice also we just did a straight line down through here. As we've seen in the past, we can have anti-disassembly techniques that would cause this kind of analysis to fail. Okay, it would miss and it would get misaligned. So a better plan would be to start at the entry point, do the first basic block and try to collect the leaders, and then for each leader we find, repeat that process, as opposed to trying to do it in a nice linear way. Why do we do this? Basic blocks simplify program analysis. They have a single entry at the top and a single point where control flows out at the bottom, and control passes sequentially through them. So you can analyze them, right? This basic block up at the top is basically, could be thought of as one function. It does some particular thing, and at the end of it, you go somewhere else. You can be wrong. We've already indicated that. Obfuscated control flow, computed branches, push returns, all those things can screw up this naive analysis. But it's still a good place to start. All right, so let's shift gears. We'll come back to basic blocks later. But let's shift gears and talk about some assorted assembly language topics. You've got enough assembly in your head now that I'm going to throw some general assembly idioms at you and some odd things that you might see so that you know them when you see them later. Zeroing out registers. So how would you do that? Well, you can move a zero into a register, but that's not something that you see very often in assembly code, as you've already know. The more common way is to exclusive OR something with itself, a register with itself, like EAX or RAX. And that will zero out the register. You could also zero out the register by subtracting the register from itself. Both of those will zero it out. And they each take exactly 2 bytes. You can see over here on this side, we started out with this, we assembled it, and then we dumped it out, and sure enough, those each take exactly 2 bytes. There's not one really benefit of one over the other. They're going to take the same number of cycles, they're going to use the same number of bytes. Basically, they're the same. The preference is really more aesthetic, and you more commonly see XOR than you do sub. But you do see sub sometimes. They also modify the flags. Is there a way to do this that does not modify the flags? Well, that's something that's worth thinking about a little bit. We know move doesn't modify the flags. So, for example, if I move a 0 into EAX, that's right, I have to overwrite this 4-byte register with a 4-byte 0. What does that look like? Well, it looks like this. Sure enough, 1, 2, 3, 4, 5 bytes are required to do this with a move, as opposed to just the 2. But on the plus side, flags don't get set, and that could be handy. Maybe I don't want flags to be set. Well, another way to avoid setting flags would be for me to push all the flags, do the operation, and then pop all the flags. So here I need a byte for push, a byte for pop, and then 2 bytes for an XOR or a sub to zero out the register. That gives me 4 bytes. I save a byte over the move, I don't modify the flags, and I still zero out the register. That's good. That's pretty cool. The best way I know of to zero out a register without modifying any flags is the trick you see here. I can push a 8-byte 0 onto the stack with 2 bytes, and I can pop it into a register with 1, and that gives me a 3-byte method for zeroing out a register without modifying any flags. There you go. Alright, so by this point you may be asking me, what is the point of this? Well, the point is that I am looking for a way to achieve an effect, zeroing out a register, without achieving secondary effects like modifying flags. So for example, if I do this, if I zero out the register in this way, and then I check the zero flag, it'll be undisturbed by these operations, and it will be whatever it was before these happened. Code like this can be used to move operations in between a comparison or some other operation that sets the flags and where I check the flags. It can be a way to obfuscate code. This is also an indication that sometimes the best way to do things in assembly isn't necessarily the most obvious. Was it obvious that a nice fast way to zero out a register without modifying the flags is to push and then pop? That's not necessarily obvious. Maybe I have a comparison. I need to zero out a register to hold some result before I check it. I want to be sure it's zero. This is a way to do that. So there's lots of little tricks like this that you'll see in assembly programs, and they get there, honestly, they get there by writing assembly to achieve an effect. Push and pop, in this case, they're used for secondary effects. You might wonder, doesn't this take a long time to push and then pop this way? And probably not. Again, this probably isn't writing out to main memory anywhere. This is probably living entirely within the processor's scope because of the way modern processors optimize these kinds of operations. Let's talk about lookup tables. So byte lookup is one way things might happen. Looking up a byte based on another byte is byte translation. So I've given a byte and I want to translate that byte into a different byte. And how would I do that? Well, this comes up a lot, weirdly enough. So over here, I want to take the bottom 4 bits of EAX and convert those into a hex digit. So those bottom 4 bits specify a nibble, and a nibble is equal to a hex digit. So I want a lookup table, and there it is, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So this, if I could index, and if I could just grab the bottom 4 bits and index into this, I would get the correct hex digit as a character. And sure enough, that's what I do. I go ahead and I AND EAX with 0xF, so this just masks off the bottom 4 bits. Then I take the address of this table, hex, and I add RAX to it. It'll be the bottom 4 bits, and so it will tell me the correct offset. I move the byte contents of that address into AL, and now I've done the conversion. Easy, very simple. This is a common enough sort of thing, or at least it used to be, that there's actually an instruction for this. There's an instruction called translate or translate byte. These are the same instruction. It's weird that there's 2 different names for them. The instruction looks up a byte in a table pointed to by RBX and loads it into AL. And again, you don't get to pick those registers. Those are the registers it uses. It just always uses those. They are implicit registers. So if you see them in a disassembly, it might lead you to think you can change those registers. You can't. It always uses those specific registers. The effect is basically to go take RBX, add AL to it, read the byte contents of memory at that address, and stick it in AL. That's what it does. Okay? That's not a real instruction because I can't do this part right here. I can't write RBX plus AL. The assembly won't let me do that because AL is an 8-bit thing and I'm only allowed to use 64-bit things in addresses. So I'd have to 0 extend AL or use RAX in this position. I have to be sure that RAX had the right stuff in it. I could have done that with the previous one, but you see what's going on here. All right, so how does this work? Well, you see over on the side, I've broken RAX up into the AL piece and all the rest. Okay, the lowest byte of RAX is given by AL. Now, I go ahead and take RBX and I add AL to it. So I take 2130, I add in this case 03 to it, and I get 2133. Then I proceed to go and look up the byte that's stored at address 2133. It's a D in this case. So I take D, and the character code for D is hex 44, and I put that into AL. Doesn't modify any of the high bits of RAX. It just modifies AL. And there you go. That's what it does. This is a single byte operation. It runs very quickly. If you do lots of lookups with respect to a single table, it can save some time, since RBX is set once to the start of the table, and then all the bytes of the table are cached if the table is aligned, because it's 256 bytes. That's much less than a page. So if it's aligned on a 256 byte boundary, it'll be all inside one page, and it'll be a very fast operation. Just remember that RBX that we're using for this is a callee saved register. So here is a routine that uses that. This is a routine that converts a value into hexadecimal, and it prints it out. How does it work? Well, up at the top, at print hex, we see that we have the normal preamble. We push RBP, we move RSP into RBP. Then I save RBX, and I push it twice. And you may wonder, why is he pushing it twice? I'm pushing it twice because I want to be sure the stack gets aligned correctly. So I push it twice. Then I take the address of hex, which is this little lookup table at the bottom, and I put it in RBX. So I'm using LEA for that, so I put this in square brackets. So I take the address of hex and I put the address in RBX. I could have also said move RBX comma hex without the brackets, but LEA is what I will typically use for this, and the reason has to do with position independent code, as you already know. Then I take RDI and I move it to RSI. What's in RDI? Well, by the calling convention, the first argument to this function would be in RDI. What about a second argument? Well, that would be in RSI, which I'm overriding. So it's reasonable to conclude that since I'm using RDI and I'm trashing RSI, this must just take a single argument, which is in RDI. Hope that makes sense to you. Then I do another LEA. I put the address of a buffer in RDI. So think about this for a minute. RSI is commonly called the source register. RDI is the destination register, and that's how I'm using them. I'm taking the argument and moving that address into the source register. I'm moving the buffer, which is where I'm going to store stuff, into RDI, or the destination register. And you see at the bottom, buffer is a little reserved area of 17 bytes. Why 17? Well, a hex number, a 64-bit hex number, is going to consist of 16 characters, right? It's 8 bytes, so it's 16 nibbles, so it's 16 hex characters. And then I have to have a terminating null if I'm going to call a C function with it, which I will. So I need to put 17 bytes down there. And I put that in BSS because I want that to be writable, and it's uninitialized data. This just tells the assembler, hey, tell the linker to reserve some bytes somewhere, and there's no content to put in them. So after that, I XOR EAX with itself, and as we already know, that zeroes it out. In fact, that zeroes out RAX. Then I put 16 into ECX. Now RCX, as you know, is the count register, and we're going to use it for that purpose here. So I put 16 in there, right? I'm going to process 16 nibbles to produce the 16 hex digits for the value that was in RDI, now in RSI. So I then put a 0 in RDI plus RCX. Whoa, what am I doing there? This is the null terminator. Remember, RDI currently points to buffer, just 17 bytes. ECX contains 16, so this is buffer plus 16. That is the 17th byte of buffer, right? Because the first byte is 0, second one's 1, The 17th one is at plus 16. And I put a 0 there. So I go ahead and null terminate the string immediately. Now I use the CIL register. And you may be wondering, what is CIL? You don't see it that often, but you'll see it quite a bit if you look at a lot of assembly code. CIL is the low byte of RSI. RSI is the source register. This is the thing I want to encode. So I move the lowest byte out of RSI and I move it into AL. Then I AND it with 0xf, so that takes off, that just gives me the low nibble, which I need to now turn into a character. And what I do is I go take RDI, that's the destination register, right? DI is the destination register, that's the address. Sorry, I skipped something. My brain is shot again. Too tired to be doing this. I mask off the low 4 bits. Then I do translate. All right. Now, what is translate going to do? It's going to take RBX, which points to hex. Right, we set it up here at the top. It's going to take RBX. It's going to add AL to it. That's going to add it and index into that little hex array down there and find the correct character. And it's going to move that character into AL. There we go. Sorry about that. Then I'm going to store that at RDI, that's buffer, plus RCX, that's our counter, minus 1. So right now the counter contains 16, and so minus 1, that would be 15, so it's going to put it at the last position. And that makes sense because we're going to go ahead and encode this, the contents of the register from from the lowest order nibble up to the highest. Okay, and we're going to put that into memory. Then we shift RSI right by 4, which means the low 4 bits are thrown away and everything shifts over. And then I loop back up to dot loop, and that will decrement RCX and compare it to 0. So we'll decrement, we'll compare, and we'll branch if we're not quite 0 yet. So we run through all of that process. Now, when RCX is 1 and we hit this loop, we'll decrement it to 0 and then terminate, which means RCX will never be 0 in the body of this loop. So do we write at the position buffer plus 0? We do, because again, this minus 1 over here. So we do in fact write all 16 positions out. Now we take the address of buffer and put it in RDI, and that is the only argument to putS. So then we call putS with respect to the PLT. We pop RBX to restore its value. We never modified the stack pointer, so we're not worried about that. And we do a leave and return. And we're done. So here's the code. We carefully follow the calling convention. The only thing we don't do is try to restore the stack pointer at the end because we don't need to. But this follows the calling convention and gives us code to print out a hex value. How would we test it out? Well, here's an example that would let us test it. Global underscore start default rel, because we want to be able to have position independent code. Extern putS, because we'll need that. We'll include printhex.asm, so the text of the thing we just wrote will be included directly right here. And then in our text section, we have an underscore start where we put a value to print in RDI, and we call printhex. That would print it out. Then we put a 16 EAX. We put ED. We zero out EDI, so we have a return value of 0, and we do a syscall, which calls exit, and we're done. That return at the end is gratuitous. I could have put a halt there. It doesn't matter. The syscall won't return. Now, here's a question for you. Is translate used? So I did a quick count across a bunch of different libraries, and sure enough, it shows up in quite a few. It shows up in JavaScript. It shows up in the GNU utils, in Wavpack, in gcrypt. It really shows up in libcrypto. Okay, and it shows up in the Qt5 web engine. It doesn't surprise me it shows up in crypto. Lots of byte-oriented manipulation in crypto libraries. And it doesn't surprise me it shows up in the Qt5 engine core. That's not that unusual. Some other instructions that we might consider. sfence is one that's basically a memory protection one. MPSA DBW is one of my favorite ones. Just because it's, mnemonics is supposed to help you remember stuff, that does nothing for me. The point of this is some instructions are more favored by particular compilers, some are not favored. There's lots of instructions that do pretty specialized stuff. And whatever code you're going to produce, it has to deal with all this. Malware authors love to put some of this obscure stuff in there. I mean, a lot of them write C now, so they don't necessarily get it. But certainly they can put this obscure stuff in there to break your analysis because it doesn't cover these weird cases. All right, let's talk about unrolling and the vector registers. We're not going to go too deep into the vector registers, to the SIMD registers, but we'll get a little experience with that here. So here's a loop. Sorry, here's actually a loop and another version of that loop. And you see what we were doing. We run through 10,000 entries in an array, and for each one we add an increment to it. The first loop does that just by running through 10,000 times. The second loop is a little different. The second loop modifies an entry, and it modifies the next entry, and it counts by 2 each time. And my question for you is one of those two better? Does it matter? Do those two matter? I mean, if you just look at the sequence of increments, we have the same number of adds happening, the same number of increments happening. It's pretty much the same thing, right? Well, let's go ahead and compile them. And when we compile them, we wind up with code that looks like what you see here. The top loop is going to execute 4 instructions every time it passes through the loop. It's going to do the add, it's going to increment RCX, compare it to 10,000, and jump if less to top. That's 1, 2, 3, 4 instructions. Yeah, they don't all take the same amount of time to execute, but it's 4 instructions every time through. It runs 10,000 times. That's 40,000 instructions that get executed for that loop. Let's look at the one below it. The one below it does 2 adds, then it adds 2 to RCX. It compares it to 10,000 and then jumps to the top. It does 1, 2, 3, 4, 5 instructions each time through, right? It still runs, it still is going to do all 10,000 entries, but it's only going to run half as often, right? Because it adds 2 each time. So it's only going to run 5,000 times. 5 instructions times 5,000 cycles is 25,000 instructions. The top one, 40,000 instructions. This one, 25,000 instructions. Wow. In addition, this branch happens every single time. This branch happens 10,000 times. This branch only happens 5,000 times. Well, really, one less than that. So 9,999, 4,999. So the branch happens about half as often as well. Does that matter? Yeah, it does. So let's write a C function and compile it and see what the compiler makes of it. So we tried it with our little hand assembled stuff, but let's actually write the code itself and see what the compiler does with it. So here's an update function. It's got this loop to 10,000 and it adds the increment each time through. And we'll disassemble it. And here's what we get when we disassemble it. That's horrific, right? Again, this is what you get when you look at unoptimized code. You get all this weird stuff with RBP, all these local variables happening. It's a mess. One thing you might not recognize is this CDQE. CDQE performs a sign extension and promotes EAX to RAX. Why is that needed? Why would you do that, right? EAX is a 32-bit value, and if it's negative, it will have the high bit, the bit 31, set to a 1. The larger RAX may have all zeros at the top. this will sign extend it so that if there is a 1 in that bit 31 position, it gets smeared across the remaining 32 bits all the way up to bit 63. Why do that? That's so we can use, since it's EAX, we can use RAX in address calculations. Remember, RAX, we have to use 64-bit things in addresses, and this promotes EAX to a full 64-bit value so we can use it. And then we do it again down here. Okay. Now, each iteration of this loop, so here's the loop, we're going to jump less than equal up here, and we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 instructions every time through. That's 170,000 instructions. That's horrible. Right? We did much better with our other stuff. Well, let's try optimizing it. So I optimize it, and this is what I get out from when I optimize it. Much better, right? 1, 2, 3, 4 instructions per iteration, or 40,000 iterations. This doesn't look like our code. Our code used RCX. This doesn't. It's worth maybe taking a little look to see how it does work. We'll notice a couple things immediately. First, we'll notice there's a NOP here, and we should be trained by now to realize that when a NOP happens, we expect this to maybe be aligned. The NOP is probably there to align an address, and sure enough, this is a 16-byte aligned address, and that's because it's the target of this branch down here, and we're optimizing, and that's better to have that aligned. Waste a little bit of memory in order to get an aligned address. Great. So we start out, we do this LEA right here, RAX, we do RSI plus this. Okay, what's going on here? Well, we know a couple of things about the stuff coming into us. We know that RDI holds the amount to increment. It's the first argument. And it's an int, so really it's just EDI. And our SI holds a pointer. It holds a pointer to the array. Now, what we're doing here is we're adding this fixed amount to RSI and putting that in RAX. And in fact, what's happening here is we're adding 10,000 entries, the length of 10,000 entries to RSI, right? Each entry is a D word, so it's 4 bytes. We're adding all of that to RAX, and this is the address one past the end of the array. So instead of counting 10,000, each time we'll just increment RSI by 4 and then compare it to RAX to see if we've reached the end of the array, and if we have not, we go back up, and if we have, we return. So that's how we check for the end of the array. Otherwise, we do exactly the same thing. Each time we go ahead and add EDI to whatever is pointed to by RSI, and that's the main thing we do. We can test the timing of these. So here's my little piece of code. We'll waste some cycles here initializing the array with random entries, and then we'll update, and we'll do the update 10,000 times. Right? This 10,000 isn't over the array. This is me updating the array, the entire 10,000 element array, 10,000 times. Because again, this is going to be fast. We need to do it enough times that we can begin to get some measure. So given that we run this 10,000 times, this little loop up here, that's inconsequential. So we do that, and then we update the 10,000 entries 10,000 times. Right? 10,000 is 10 to the 4th. 10,000 times 10,000 would be 10 to the 8th. So that's a decent number of operations. Now, all things being equal, we might reasonably expect about a factor of 4 speed up from our initial 170,000 down to our 40,000, and we can try that. And it turns out when we run the naive version, right, the one without any optimization, it takes about 676 milliseconds. And when we run it with optimization, it takes about 93 milliseconds. We get a factor of 7 speed up. That's great. That's huge. And the speed up comes not just because of this, of reducing the. It's more than just going from 170,000 down. It's reducing all that memory operations that were taking place in the other one. So we get a speed up from that as well. Just a massively improved code. Value of optimization. Suppose we unroll the loop once. And we can do that. We can do that in C. And so we rewrite our C code to look like what we saw earlier. We run again from 0 up to 10,000. We bump by 2 each time. And we do 2 adds in here. That, when we compile it and look at it, that produces code that's almost identical to the original code. Again, we compute the address of the endpoint. We then do 2 adds, right, at RSI and at RSI plus 4, because double words are 4 bytes. We add 8 to RSI, compare it, and then branch if we're not equal. So, great. How does that perform? When we run that, we find that it cuts the time in half, roughly, over our previous optimized version. Yes, loop unrolling improves the performance. Great. That's great. Can't we get the compiler to do that? We can. We can add -f unroll loops, and that will unroll the loop for us. And when we do that, this is what our program ends up looking like. Again, we locate the endpoint and put it in RAX. We have a NOP here because of alignment, and then we do 1, 2, 3, 4, 5, 6, 7, 8 adds each time through. Then we add hex 20, right? 8 times 4 is 32, which in hexadecimal is 2 times 16, so in hexadecimal it's 20. We compare it and we branch if it's not the same. So it's really unrolled it. And so each time through the loop, it starts here, we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instructions, but we only run through it 10,000 divided by 8 times. And we run that, this unrolled loop does just about the same as our once unrolled version, about almost exactly the same amount of time. So that's great. And we didn't have to unroll it ourselves. We had the compiler do unrolling for us. Don't assume this is always going to make your program faster. Loop unrolling is one of those techniques that you need to understand to use. There are some weird corner cases where it can make things worse. It seldom will. Just be aware of it. Another thing we might do is try to use SIMD stuff, single instruction, multiple data. I'll do a single instruction, but I will operate on multiple D words at once. And so for this example, we're going to use the XMM register. An XMM register holds 128 bits. That is 16 bytes. A double word is 4 bytes, so that holds 4 double words. So if I can operate on XMM registers, I can operate on 4 double words at once. Now, I'm not going to go too deeply into how to use the SIMD registers because it gets really complicated really fast. But I can go through some of the high points of this code to let you know what's going on. EDI is still my increment value, but in this case, I move it into XMM2. This is fine. I can move a double word into XMM2. XMM2 now holds the value that was in EDI. And then I do a shuffle. So this guy right here is a very complicated instruction. But the net effect of this instruction is that I take the contents of XMM2, which holds EDI, and I copy it into the 4 double words contained in XMM1. So XMM1 now holds 4 copies of EDI. So the first 4 bytes of XMM1 holds what was an EDI. The next 4 holds what was an EDI. The next 4 and the next 4 hold what's an EDI. So a little vector of 4 elements, each of which is initialized to the values in EDI. Then I play the same game that the compiled versions have done, except this time I put in RCX, RSI plus 10,000. So this will be the address of the endpoint, so I can just compare at the endpoint here. And in fact, that's what I'll do down here at the bottom. I'll compare RSI, which is what I'll be using, to RCX, and that's how I'll know to terminate. Great. So now I enter the loop, and I align the loop on a 16-byte boundary. Right, I'm learning from looking what the compiler does. And I do a move DQU. So what does that do? That's going to take whatever is pointed to by RSI, and it's going to move those 16 bytes into XMM0. Now remember, those 16 bytes are coming out of the array. That's going to be the next 4 D words that are in the array, and it's going to move all of those 4 D words into XMM0. Then I'm going to add XMM0 and XMM1, so that's going to apply the increment to every individual D word, right? It's P add D. See the 3 D's there? P add D, so it knows to do double word addition. And after that, I'll write them back out. So now I'll do a move UPS of XMM0 back into RSI. I've now worked on 4 double words, so I add 16 to RSI, compare it to RCX, and if I'm not there yet, I loop around. Now, another thing I could have done to optimize this a little more, I could have made sure things are aligned and used aligned versions of move to do that work. Slight improvement, probably not much at this point. When I do all of this, and I assemble this, and I run it, what do I get? My time drops down to just 10 milliseconds. That's a significant improvement. So let's go back. I was at 48 milliseconds with what the optimization gave me. Now I'm about 1/5 of the time, right? You would expect it to go down by a factor of 4 because we're doing 4 at once, but again, we're reducing the number of times we hit a conditional branch, and so we're getting a little more than a factor of 4 speed up, almost a factor of 5. Really, really fast. This is about as fast as we're going to get this operation. All right, new homework. Step 1 here. I want you to go use objdump, readelf, GDB, whatever you like to use. I don't care, in this case, what you use. And I want you the information from the prior lecture on the C runtime to go and find main. So we talked about how to find main when we talked about the entry point, and then something got moved into RDI and how that mapped into the AMD64 ABI, all that good stuff. Go and use that to figure out the offset of the main function for user bin cat. So that's the cat executable on your system. You want the offset in the file, not the address at runtime, which gets relocated. All right. So if you're using GDB, just be aware of that. So preferably you'll be able to use objdump and readelf, and you'll be able to figure it out that way. If you end up with an address that starts with a whole bunch of 5s, you've gotten the wrong answer, and you're probably doing it in GDB, and you're not taking into account some of that stuff. You've let it start your program. Don't let it start your program. Then for step 2, I want you to use objdump, and I want you to produce a disassembly of the first 256 bytes of main. How do I do that? Well, you'll do that because you'll know the address, and so when you run objdump, you can tell it where to start disassembly, and you can give it a range and produce just those disassembly of those first 256 bytes. Put that in the text file named main.txt. That is the answer. That's your homework. Some hints. Go find the entry point. The code of the entry point is going to call libc start main that we talked about last time. The first argument to libc start main is the address of the main function. That's going to be in a register. So go look where that register is set. Use the command on the next slide to generate the disassembly. All right. You can do this with object dump alone, or you can use other tools to see how that goes. To disassemble the first 256 bytes in file, starting at, for example, that address, and save it in main text, you would use that command right there. Notice the start address and the end address. Okay. In this case, 256 in hex is 100. So we go from 34E4 to 35E4. Okay. And we -D for disassemble, and we save the result in main.txt. And that's it. You'll know one hint that you're looking at the right stuff is that you'll see an NBR64 instruction. Okay, but you'll see that if you look at the entry point too. Just be careful, look what you get, and use some sanity checking to be sure it makes sense. That's it.